At the very beginning of time, there was no universe as we know it today. There was no space, no stars, no galaxies, no planets, nothing at all. The idea of nothing can be hard to grasp, especially since we live in a world filled with everything we can see, touch, and experience. But imagine, if you can, a time before time itself, when the universe did not exist. This moment, this before, isn't a moment in time we can easily relate to, because time itself hadn't been born yet. There was no clock, no ticking seconds, no past or future. There was no space in which to have any thoughts or events. It was a complete absence, an infinite void, where no matter existed, no light, no energy, nothing. This is where the story of the universe begins. How did it all begin then? How did nothing become something? The answer lies in the heart of what scientists call the Big Bang, an event that occurred around 13.8 billion years ago. The Big Bang wasn't an explosion in the sense that we might imagine, a sudden burst of energy that sent out pieces of matter into a pre-existing space. Instead, it was an event that created both space and time. The universe wasn't simply born in a pre-existing space, it created space itself, and it all started with an extremely dense, hot, and tiny point. Think about this for a moment. All the matter, energy, and space that make up everything we know today were once compressed into a single point that was infinitesimally small. If you could have held this point in your hand, it would have been too small to even see. It was smaller than an atom, yet within this tiny, dense point lay the seeds of everything, every galaxy, every star, every planet, and every person who would ever exist. What was inside this tiny point? It wasn't a solid object as we think of things today. It wasn't like a tiny pebble or a grain of sand. This point was made up of a concentrated amount of energy and matter, compressed into a state we could hardly imagine. This energy wasn't just a thing that existed. It was all there was. It was the essence of everything that would ever be, waiting to expand and evolve. The birth of the universe was not a gradual event, but a rapid, explosive one. The moment of the Big Bang was an extremely chaotic event, one where temperature and pressure were beyond anything we can experience. Imagine the hottest fire you've ever seen, multiplied by 1 billion times. This energy-filled point exploded, and in an instant, everything changed. The universe was born, not with a bang as we might picture, but with an incredibly rapid expansion. The point grew in size by an unimaginable factor, what we call cosmic inflation. In the first moments after the Big Bang, the universe expanded faster than the speed of light. Yes, that's right. The universe stretched faster than the speed of light itself, which is mind-boggling because nothing can travel faster than light. But the fabric of space itself can stretch. And in those early moments, it stretched exponentially, creating more and more space as it expanded. This inflationary period was incredibly brief, but it had a profound impact on the universe. As the universe grew, it cooled. It went from being an infinitely hot, dense mass to a much cooler, more expansive space. In this cooling process, matter began to form. Atoms, the basic building blocks of matter, began to form for the first time. Before this, there were no atoms, there were no particles, there was only energy. But as the universe cooled, protons, neutrons, and electrons, fundamental particles of matter, came together to form the first elements. The universe was now filled with basic hydrogen and helium atoms, the simplest elements in the periodic table. But even though the universe was now made of matter, it wasn't yet a place where stars could shine or life could exist. The universe was still too young, too hot, and filled with a glowing fog of particles and light. It took about 380,000 years for the universe to cool enough for light to travel freely. This is when the first light appeared. This light was not like the light we see today. It was the glow of the earliest form of radiation, known as the cosmic microwave background radiation, CMB. The CMB is like the afterglow of the Big Bang, a faint ancient light that still exists today and is detectable by modern instruments. This light allowed scientists to peer into the early universe and study its origins. It's like looking into a cosmic photograph of the universe when it was just a baby, full of potential but still in its infancy. But how did the universe go from being a hot, glowing fog to the vast, organized cosmos we see today? Well, after the formation of basic atoms, gravity began to take over. Gravity is the force that pulls matter together, and in the early universe, it was this force that began to create the first stars and galaxies. In those early years, gravity caused hydrogen and helium gas to collapse into dense clouds, which then ignited into the first stars. These stars were the first generation of cosmic furnaces that would eventually give birth to heavier elements like carbon, oxygen, and iron, elements that are essential for the formation of planets, life, and even our own existence. So, what's the key takeaway from this first chapter of our universe's story? The universe was born out of nothing. Well, nothing in the sense that there was no matter, no energy, no space, nothing at all. But then, from this blank canvas, everything that we know and experience today began to unfold. The Big Bang set the stage for everything to come. And even though we can never truly comprehend the scale and speed at which it all happened, we can study its effects, which still resonate today in the universe's expansion, in the cosmic radiation that surrounds us, and in the stars that continue to shine. The universe, once confined to a tiny point, began to unfold and expand in ways that we are still uncovering. The story of how nothing became everything is far from over. It's a story that continues to evolve as the universe itself evolves. And as we explore the cosmos, we uncover more and more about how this incredible journey from nothing to everything continues to shape the world around us. The Big Bang Theory, one of the most widely accepted explanations for the origin of the universe, is more than just an idea. It's the cornerstone of modern cosmology. But what exactly is the Big Bang? And what does it tell us about how the universe began? The term Big Bang might sound like an explosion, but in truth, it was not an explosion in the way we typically imagine one. It wasn't like a bomb going off, with debris flying through a pre-existing space. The Big Bang was, in fact, an expansion, a rapid stretching of space itself. Before the Big Bang, there was no space. Space didn't exist, and neither did time. To truly grasp this, we have to understand that the Big Bang created both time and space. Around 13.8 billion years ago, the universe began as a single incredibly hot and dense point, sometimes referred to as a singularity. This singularity contained all the energy and matter of the entire universe, compressed into an infinitesimally small space. It was so dense that it could hardly be considered anything we would recognize as a thing in the traditional sense. This tiny, dense point was not something that existed in space. It was space, and everything we now understand about the cosmos, gravity, light, time, and space itself, came into being with it. The Big Bang was the beginning of everything, but it wasn't a single event that happened in a single spot in space. It was a cosmic event that occurred everywhere at once. The universe didn't expand from a particular point. It expanded everywhere simultaneously, meaning every point in the universe was once at the center of the Big Bang. This concept is fundamental to understanding the Big Bang and why it's not a localized explosion, but rather the beginning of space itself. At first, the universe was incredibly small, smaller than the size of an atom. The temperature was unimaginably high, and the density was beyond anything we can experience today. Matter and energy were indistinguishable at this point. The laws of physics, as we understand them, didn't yet exist in any recognizable form. But as the universe began to expand, it cooled rapidly. In the first moments, the temperature dropped from millions of degrees to just thousands of degrees, allowing particles to form. The first few moments of the universe. The first few minutes of the universe were incredibly chaotic. During this period, particles like protons, neutrons, and electrons began to form. These subatomic particles, which make up atoms, were created in extreme conditions. The density of the universe was so high that particles were constantly colliding, and the temperature was so hot that no atoms could remain intact for long. For the first few seconds, the universe was an intense sea of plasma, a hot soup of free electrons, protons, and neutrons moving at almost the speed of light. As the universe continued to expand, the cooling allowed these subatomic particles to begin sticking together, forming the first atomic nuclei. In the first few minutes, these nuclei were primarily made up of hydrogen, helium, and a small amount of lithium. But it wasn't until much later, about 300 Mertirian years after the Big Bang, that these atoms were able to bond with electrons to form the first fully stable atoms of hydrogen and helium. This era, known as recombination, allowed light to travel freely for the first time, which was a game-changer for the evolution of the universe. Cosmic inflation, a rapid expansion. One of the most fascinating and surprising features of the Big Bang is something known as cosmic inflation. This theory proposes that in the first tiny fraction of a second after the Big Bang, the universe expanded at an incredibly rapid rate, faster than the speed of light. This expansion lasted for only a fraction of a second, but it was essential in shaping the universe we know today. Cosmic inflation helped explain why the universe looks so uniform on large scales and why the temperature of the cosmos is so consistent throughout space. At this early moment, the universe was so small that it was only about the size of a single particle. Yet, in less than a trillionth of a second, the universe expanded by a factor of more than 10^26. Imagine something growing from the size of a golf ball to the size of the observable universe in just one blink. This rapid expansion caused the universe to cool and spread out. During this period, the universe was dominated by the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. But the universe was still incredibly hot, far too hot for the formation of stars or galaxies, or even for atoms to hold together for any significant time. The formation of light and the cosmic microwave background. After inflation slowed down, the universe continued to cool and expand. It was still a glowing ball of plasma, too hot and dense for light to travel through. But as the universe cooled enough to allow electrons to combine with protons to form neutral hydrogen atoms, the universe became transparent for the first time. The moment this happened, light could finally travel freely through space, and the first light in the universe was released. This light, which is still present today, is known as the cosmic microwave background radiation, CMB. The CMB is like a snapshot of the universe when it was just 380,000 years old, and it has been traveling through space ever since. Modern telescopes, such as the Planck Observatory, have been able to detect this ancient light, and scientists have used it to map the temperature and structure of the EQ universe at that time. By studying the CMB, we can look back at the early universe, understanding how matter was distributed and how it led to the formation of galaxies, stars, and eventually the planets we live on today. The role of dark matter and dark energy. While we now understand how matter formed after the Big Bang, there are still many mysteries that remain unsolved. One of the biggest questions revolves around dark matter and dark energy, two strange and invisible forces that make up about 95% of the universe, yet remain largely undetectable. Dark matter, which is thought to account for roughly 27% of the universe's mass, doesn't emit, absorb, or reflect light, which is why we can't see it directly. However, its existence is inferred from the gravitational effects it has on visible matter. It helps keep galaxies together and influences the motion of galaxies within clusters. Without dark matter, galaxies wouldn't have enough mass to hold together, and the universe as we know it wouldn't exist. Dark energy, on the other hand, is an even more mysterious force. It accounts for about 68% of the universe's energy and is responsible for the accelerating expansion of the universe. This force pushes galaxies apart at an ever-increasing rate, making the universe grow larger and larger over time. While we know that dark energy exists, scientists have no idea exactly what it is or how it works, and it remains one of the biggest mysteries in cosmology. Understanding the Big Bang. A continuing journey. The Big Bang theory is a powerful model that explains the origins of the universe, but it's not a theory that answers all our questions. In fact, the Big Bang leaves many mysteries to be explored. For instance, How did the laws of physics come into being? What happened before the Big Bang, if time itself began with the event? What is the ultimate fate of the universe, and how will it end? These are questions that scientists are still working to answer. The Big Bang Theory is also a constant reminder that the universe is always changing. The galaxies are moving farther apart, stars are being born, and others are dying. Our universe is alive, and we are just beginning to scratch the surface of its true story. So, where does that leave us? We know that the universe started from an incredibly small, hot, and dense point, an event that created everything we see around us today. The Big Bang wasn't just the beginning of stars and planets, it was the birth of time and space. And while there's still so much we don't understand, the Big Bang continues to shape the way we view the cosmos. As we peer deeper into the universe's past, we may just find even more evidence of how this incredible journey from nothing to everything began. The early universe, after the Big Bang, was a place unlike anything we can imagine today. It was hot, dense, and filled with intense energy, a chaotic sea of particles that would eventually give rise to everything we know: stars, planets, galaxies, and life itself. In the first moments of the universe, everything was in flux, and the laws of physics as we know them had yet to take shape. After the Big Bang, the universe began expanding at an astonishing rate, stretching and cooling as it went. This rapid expansion, known as cosmic inflation, happened in just a fraction of a second. The temperature of the universe was incomprehensibly high, billions of degrees, during these first few moments, which meant that atoms or even atomic particles couldn't form. Instead, the universe was filled with a hot, dense soup of particles, protons, neutrons, and electrons, all constantly colliding and interacting at unimaginable speeds. At this point, the universe was still incredibly small, but it was already beginning to change. What happened during these first few moments that allowed matter to begin to form? To understand this, we need to look at the four fundamental forces that govern the universe: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. At the time, the universe was so hot that these forces were unified into a single force. But as the universe cooled, these forces began to separate, each taking on its own role in shaping the cosmos. The formation of subatomic particles. In the immediate aftermath of the Big Bang, the universe was a hot, dense plasma. It was too hot for atoms to form. There was simply too much energy for atoms to hold together. Instead, there were only free-floating subatomic particles. These were the building blocks of matter, but they couldn't stick together yet. For the first few moments, the universe was a roiling sea of particles, protons, neutrons, and electrons, constantly interacting and breaking apart. This period, known as the quark-gluon plasma stage, lasted only a fraction of a second, but was critical to the formation of the universe. In this plasma, quarks, the fundamental building blocks of protons and neutrons, and gluons, particles that mediate the strong force, were moving freely, unable to combine into stable particles because of the extreme temperatures. As the universe expanded and cooled, things began to slow down. This cooling process allowed particles to combine and form more stable structures. After just a few seconds, the universe was still incredibly hot, but it had cooled enough for protons and neutrons to start forming. These particles then began to bind together to form the first atomic nuclei. But even though the basic components of matter were coming together, the universe was still too hot for stable atoms to exist. The formation of hydrogen and helium, nuclei. A few minutes after the Big Bang, the temperature dropped enough to allow nuclear fusion to occur. During this period, known as Big Bang nucleosynthesis, protons and neutrons fused together to form the nuclei of the lightest elements, hydrogen, helium, and a small amount of lithium. These nuclei were the first matter to form in the universe, and they would go on to play a crucial role in the formation of stars and galaxies later on. The universe, in its infancy, was dominated by hydrogen, the simplest and most abundant element. Helium was the second most abundant, and a trace amount of lithium was also present. At this point, the universe was still a hot, glowing ball of particles, and it wasn't until hundreds of thousands of years later that the temperature dropped enough for light to travel freely through space. This is where things get interesting. These early moments of nuclear fusion set the stage for the formation of everything we see today. All of the elements necessary for life, including carbon and oxygen, would eventually be forged in the hearts of stars. But for now, the universe was still very young, and these first elements of hydrogen and helium were all that existed. The universe begins to cool. As the universe continued to expand and cool, things started to change. After about 380,000 years, the universe had cooled enough for electrons to combine with protons to form the first neutral atoms. This moment, known as recombination, was a turning point. For the first time, the universe became transparent to light. Prior to this, the universe had been a hot, dense fog, with light constantly scattering off free electrons. But when atoms formed, light could finally travel freely through space. This was the moment that light as we know it, photons, could travel without being constantly scattered by particles. This was also when the cosmic microwave background, CMB, was released. The CMB is a faint glow of radiation that still exists today, and it is a critical piece of evidence for the Big Bang theory. By studying the CMB, scientists can peer back into the early universe and study its origins. The CMB is the oldest light we can detect, and it provides a snapshot of the universe when it was just 380,000 years old, an infant in cosmic terms. The emergence of light. This moment, when the universe cooled enough for light to travel freely, was a defining moment in the history of the cosmos. Before this, the universe was a hot, glowing ball of plasma, filled with energy, but no light as we understand it. After recombination, the universe became transparent to light, allowing photons to travel freely across space. This light, known as the cosmic microwave background radiation, is a relic of the early universe and a crucial piece of evidence that confirms the Big Bang theory. But while the universe was now filled with light, it was still a cold and dark place in terms of visible stars and galaxies. This early universe was still extremely young, and it would take hundreds of millions of years before the first stars and galaxies began to form. Still, the first light, the cosmic microwave background, was a pivotal milestone, one that marked the universe's transition from a hot, opaque state to a transparent one. The formation of the first structures. As the universe continued to expand and cool, regions of slightly higher density began to form. These denser regions became the seeds for the first stars and galaxies. The early universe was a place of primordial chaos, but gravity began to take over. Gravity, the force that pulls matter together, began to shape the universe by pulling gas clouds of hydrogen and helium together. Over the next few 100 million years, these clouds began to collapse under their own gravity, eventually reaching temperatures and pressures high enough to ignite the first stars. These stars, known as the first stars or population 3 stars, were massive and short-lived, burning through their fuel at a rapid pace. But in their short lifetimes, they played a crucial role. They forged heavier elements in their cores, elements like carbon, oxygen, and nitrogen, which are essential for life as we know it. The first stars marked the birth of a new era in the universe, one that would eventually lead to the formation of galaxies, solar systems, and even life on Earth. But before that could happen, the universe had to go through a series of steps, each one more complex than the last. It was during this time that the first galaxies began to take shape, and the universe began to resemble the cosmos we know today, only much, much younger. The formation of galaxies. By around 500 million years after the Big Bang, the first galaxies began to form. These galaxies were collections of stars, gas, and dark matter, all bound together by gravity. Some of these early galaxies were small and irregular, but over time, they merged and grew, eventually forming the large spiral galaxies we see today. As the first stars died, they exploded in supernovae, spreading the heavier elements they had created into the surrounding space. These elements, such as carbon, oxygen, and iron, would eventually become the building blocks for future generations of stars, planets, and life itself. The birth of the first stars was one of the most significant milestones in the universe's history. It marked the beginning of a process that would go on to shape everything we know today: galaxies, solar systems, and the very elements that make up the Earth and life itself. But how did these stars form, and what were the conditions that allowed this process to begin? After the universe cooled enough for atoms to form, the cosmos was filled mostly with hydrogen and helium, the lightest elements. For hundreds of millions of years, this gas remained largely undisturbed, drifting through the vast emptiness of space. The universe, though filled with matter, was still dark and quiet. There were no stars yet, no galaxies, just a vast empty void punctuated by small clouds of hydrogen and helium. However, gravity had already begun to play its part, and it was the force of gravity that would soon kickstart the process of star formation. Gravity's role in star formation: gravity is the force that pulls matter together, and in the early universe, it played a key role in bringing hydrogen and helium gas into dense clumps. These clumps of gas were the first building blocks for stars. As gravity pulled more and more gas into these dense regions, the material began to collapse inward, causing the gas to heat up as it compressed. The process of gas collapsing under its own gravity is known as gravitational contraction. As the gas cloud grew denser, the temperature and pressure in the center of the cloud increased. This is the first step in the formation of a star. The core of the collapsing gas cloud grew so hot that nuclear fusion reactions began to occur. This process releases an enormous amount of energy, and it was this energy that marked the birth of the first stars. The birth of the first stars. The first stars, often called population 3 stars, were born about 200 to 400 million years after the Big Bang. These stars were vastly different from the ones we see today. They were much larger and hotter, burning through their fuel at a much faster rate. These stars were giants, perhaps up to 100 times the mass of our Sun, and they lived fast and died young. Because they burned their fuel so quickly, their lifespans were incredibly short, only a few million years compared to the billions of years we expect from modern stars. These first stars were made almost entirely of hydrogen and helium, with little to no heavier elements, what we call metals in astronomical terms. This lack of heavier elements meant that these stars had a different chemistry than modern stars, which are made up of elements like carbon, oxygen, and iron. As a result, the first stars were incredibly hot and luminous, far outshining any stars we see today. The role of supernovae in element formation. The first stars were not just brilliant points of light in the cosmos. They were also responsible for creating many of the elements that would eventually form planets, stars, and even life. As these stars lived and died, they exploded in cataclysmic events called supernovae. When a massive star reaches the end of its life, it can no longer support the weight of its own gravity. The core collapses, and the outer layers of the star explode outward, releasing vast amounts of energy. This explosion scatters the elements that were created inside the star into the surrounding space, enriching the interstellar medium with elements like carbon, oxygen, nitrogen, and iron. These elements, forged in the hearts of the first stars, would go on to become the building blocks of future generations of stars and planets. Without these early supernovae, the universe would have been made almost entirely of hydrogen and helium, and the complex chemistry needed for life, as we know it, would never have been possible. Supernovae were not just the deaths of stars, they were the birthplaces of new materials, spreading the ingredients necessary for the formation of planets and eventually, life. The role of dark matter in star formation. While we can observe the formation of stars through their light, there are other factors at play in the formation of these cosmic objects that are more difficult to detect. One of the most important of these is dark matter, a mysterious and invisible form of matter that makes up about 27% of the universe. While we can't see dark matter directly, scientists know it exists because of its gravitational effects on visible matter. Dark matter played a crucial role in the formation of the first stars and galaxies. Its gravity helped to pull matter together, aiding in the collapse of gas clouds that would eventually form stars. In fact, it's thought that dark matter was a key ingredient in the formation of the first galaxies, acting as a sort of cosmic scaffolding. These clumps of dark matter provided the gravitational pull necessary to bring together the gas and dust that formed stars and galaxies in the early universe. Without dark matter, the process of star formation would have been much slower, and it might have been much harder for the first stars to form at all. This invisible substance remains one of the greatest mysteries in cosmology, and scientists are still working to understand its true nature and how it works within the universe. The formation of galaxies. As the first stars began to shine, they didn't exist in isolation. They were part of larger structures, galaxies. A galaxy is a massive gravitationally bound system of stars, gas, dust, and dark matter. The first galaxies were small and irregular, and they began to form around 500 million years after the Big Bang. These early galaxies were the birthplaces of the stars that would go on to populate the universe. The process of galaxy formation was influenced by both visible matter, like gas and stars, and invisible matter, like dark matter. Dark matter formed massive structures called dark matter halos, which acted as the gravitational scaffolding for the gas clouds that would eventually form stars. These early galaxies were small and chaotic, but over billions of years they merged and evolved into the large structured galaxies we see today, such as the Milky Way. Star clusters and stellar nurseries. Within these early galaxies, stars didn't form in isolation. Instead, they often formed in groups, star clusters. A star cluster is a group of stars that are born from the same gas cloud and are bound together by gravity. There are two types of star clusters, open clusters and globular clusters. Open clusters are relatively young and contain stars that are still in the process of forming, while globular clusters are older, with stars that have already evolved and aged. One of the most fascinating aspects of early star formation is the concept of stellar nurseries, regions in space where gas and dust clouds are dense enough to give birth to stars. These nurseries can be found in many galaxies, including our own, and they are the sites where new stars are continually being born. The formation of stars within these nurseries is driven by gravity, which causes the gas and dust to collapse and heat up, eventually leading to the ignition of nuclear fusion. The importance of the first stars. The first stars were the pioneers of the universe. They created the elements that would go on to form planets, and their violent deaths in supernovae seeded the cosmos with the raw materials necessary for life. These stars were the first step in the ongoing process of cosmic evolution. Without the first stars, there would be no galaxies, no planets, and no life. As the universe continued to evolve, new generations of stars formed from the materials created by the first stars. These new stars were made from a richer mix of elements, allowing them to burn at different temperatures and produce a wider variety of chemical elements. Over time, the universe became more complex, and the conditions necessary for the formation of planets like Earth began to take shape. The first stars set the stage for everything that followed. They were the first light in the universe, the first sparks of energy and matter that would eventually lead to the creation of galaxies, planets, and the very conditions necessary for life. The formation of stars was only the first step in the creation of the complex, vast universe we see today. As these first stars began to shine, their gravitational influence helped pull together the surrounding gas, dust, and dark matter, forming larger structures known as galaxies. But how did these galaxies come to be, and what role did they play in shaping the universe? After the birth of the first stars, around 200 million years after the Big Bang, the universe was still a vast, dark place. But over the next several hundred million years, gravity began to pull together the scattered particles of gas and dark matter, eventually giving rise to the first galaxies. These early galaxies were not the large, spiral galaxies we are familiar with today, but small, irregularly shaped collections of stars and gas. Their formation was not an isolated process, but was shaped by both visible matter, like stars and gas, and invisible matter, like dark matter, which played a crucial role in their creation. Gravity and dark matter in galaxy formation. At the time, the universe was still mostly composed of hydrogen and helium, with dark matter playing a key role in the formation of large structures. Dark matter, which doesn't emit light but exerts gravitational pull, helped shape the first galaxies by acting as a scaffolding to gather visible matter. This unseen substance played a crucial role in the early formation of galaxies by providing the gravitational pull necessary to clump together gas and dust. Without dark matter, the process of galaxy formation would have been much slower and less efficient. These dark matter halos provided a framework around which normal matter could collect and condense. The first stars, formed in the densest regions of these dark matter halos, then began to shine and push away surrounding gas and dust with their intense radiation. Over time, the clumps of gas and dust would merge, and the first galaxies began to take shape. The interaction between gravity and dark matter, along with the radiation from the first stars, would drive the evolution of galaxies over billions of years. The early types of galaxies. The first galaxies were likely small and irregular in shape, composed of a chaotic mix of stars, gas, and dust. These early galaxies were very different from the large, well-organized galaxies like the Milky Way that would come later. They were often referred to as population 3 galaxies, named after the first generation of stars that formed inside them. These galaxies were small, compact, and lacked the complexity that we see in more mature galaxies today. As the first stars died in massive supernovae, they scattered heavier elements like carbon, oxygen, and nitrogen into the surrounding space. This enriched the gas clouds that surrounded these galaxies, giving rise to future generations of stars with more complex compositions. These second and third generation stars were much cooler and smaller than the first stars, but they were still much more stable and long-lived. As these new stars formed, they began to settle into more regular, spiral, and elliptical shapes, and galaxies began to resemble those we recognize today. Galaxy mergers and growth. As these first galaxies continued to evolve, they didn't stay isolated. The universe was filled with a vast sea of gas, dust, and dark matter, and the force of gravity continued to pull objects together. Over billions of years, galaxies began to collide and merge, forming even larger galaxies. These mergers were often violent, causing the stars within the galaxies to be tossed around in unpredictable ways. But while individual stars rarely collided, these mergers often triggered intense periods of star formation, creating bursts of new stars. These collisions and mergers are not a rare event in the universe. In fact, galaxies continue to merge today. Our own Milky Way galaxy, for example, is in the process of merging with the Andromeda galaxy, which is expected to happen in about 4 billion years. This process of galaxy merging played a key role in shaping the galaxies we see today, allowing them to grow in size and complexity over time. The role of supermassive black holes. Another important feature of early galaxies was the presence of supermassive black holes at their centers. These black holes are millions to billions of times more massive than the Sun and play a central role in the formation and evolution of galaxies. It's believed that these supermassive black holes formed in the early stages of galaxy formation and were critical in shaping the growth of their host galaxies. As gas and dust were pulled into the center of galaxies by the gravitational force of these black holes, they heated up, emitting intense radiation and creating the energy seen in active galactic nuclei, AGN. These regions, where black holes are actively accreting material, are some of the brightest and most energetic objects in the universe. In fact, the first supermassive black holes may have formed from the collapse of giant clouds of gas, and they played a key role in driving the evolution of the galaxies they inhabited. The energy released by supermassive black holes could have influenced the formation of stars in their host galaxies. Some scientists believe that the intense radiation emitted by these black holes may have heated the surrounding gas, preventing it from collapsing and forming new stars in certain regions. This process is known as feedback, and it plays a crucial role in regulating the growth of galaxies and the formation of stars. The formation of the Milky Way and other large galaxies. Over time, smaller galaxies continued to merge and grow, eventually forming the large spiral galaxies we see today, including our own Milky Way. The Milky Way is a barred spiral galaxy with a central bulge of stars, a flat disk filled with stars, gas and dust, and spiral arms that extend outward. It contains about 100 to 400 billion stars, as well as countless planets, comets, asteroids, and other celestial bodies. The Milky Way, like other large galaxies, formed over billions of years through the merging of smaller galaxies and the accumulation of gas and dust. As the Milky Way grew, it began to take on a distinct structure. Over time, its central bulge became more compact and its spiral arms began to take shape. The gravitational forces at work in the Milky Way continue to drive the formation of new stars, as well as the movement of stars and other objects within the galaxy. The expanding universe and the role of dark energy. The universe continues to expand to this day, and this expansion has a profound effect on the way galaxies are distributed across the cosmos. In the early universe, galaxies were much closer together, but as the universe expanded, galaxies were pushed farther apart. The force driving this expansion is dark energy, a mysterious substance that accounts for about 68% of the universe's total energy content. While we don't fully understand dark energy, we know that it is causing the universe to expand at an accelerating rate. As galaxies continue to expand, they move farther apart, and some galaxies may eventually move beyond the reach of our telescopes. The expansion of the universe means that over billions of years, many galaxies will become isolated from one another. But even as the universe expands, galaxies will continue to evolve. They will collide, merge, and form new galaxies, ensuring that the cosmic dance of galaxy formation and evolution continues for billions of years to come. The future of galaxies. Looking forward, the evolution of galaxies will continue to unfold. As galaxies merge and interact with one another, new generations of stars will be born and old stars will die. The merging of galaxies will lead to the formation of even larger galaxies, and the process will repeat itself for billions of years. In about 4 billion years, the Milky Way and the Andromeda Galaxy are expected to collide, forming a new, larger galaxy. This event, though catastrophic for the stars in both galaxies, will be a part of the ongoing process of cosmic evolution. But galaxies will not grow indefinitely. Eventually, after many billions of years, they will run out of gas to fuel new star formation. The stars that remain will burn out, and the galaxies will fade into darkness. However, this is a far-off event, millions of years into the future, and it's likely that by then, new processes and discoveries will have shaped our understanding of the universe in ways we can't yet imagine. Our story now turns to a much smaller but no less significant event in the grand history of the universe, the formation of our own solar system. It's hard to imagine that the Earth, with its oceans, mountains, and forests, and the Sun, the life-giving star at its center, all began as a cloud of gas and dust drifting through space. Yet, that is exactly how our solar system came into existence, through a series of events that took place over billions of years. The formation of the solar system occurred around 4.6 billion years ago, when the universe was already over 9 billion years old. The process that led to the creation of our sun, planets, moons, and other objects in the solar system started with a molecular cloud, a massive cold region of space filled with gas and dust. These clouds are often referred to as stellar nurseries because they are the birthplaces of new stars and planetary systems. The collapse of the molecular cloud. At the heart of every solar system lies a star, but before the sun could form, the materials needed to make it had to come together. In the case of our solar system, the process began with the collapse of a molecular cloud. These clouds are primarily made of hydrogen and helium, but they also contain heavier elements that formed in earlier generations of stars. This cloud of gas and dust began to collapse under the influence of gravity. As the material gathered together, it started to heat up, and the cloud began to spin faster. The collapse of the molecular cloud wasn't a random event. It's thought that something, likely a nearby supernova or a collision with another cloud, triggered the collapse. When a section of the molecular cloud began to collapse, it pulled in more and more material, creating a region of increasing density. This region became the proto-sun, the precursor to our sun. The formation of the proto-sun. As the cloud continued to collapse, the material at the center of the cloud began to heat up due to the intense pressure. Over time, this led to the formation of a dense, hot core, what would eventually become the sun. The surrounding material continued to spin and flatten into a disk, creating what we call a protoplanetary disk. This disk contained the gas, dust, and ice that would eventually come together to form the planets, moons, asteroids, and other objects in our solar system. In the early stages of the solar system's formation, the protosun was not yet a fully formed star. It was still in the process of gathering material and heating up. This stage in the sun's formation lasted for millions of years. But as the protosun grew hotter and denser, it eventually reached a point where nuclear fusion began in its core. This was the moment when the sun truly came to life, releasing a flood of energy and light into space. The energy produced by nuclear fusion in the sun's core helped to clear away much of the surrounding gas, and the sun's strong solar wind began to push the remaining material in the protoplanetary disk into the regions where the planets would eventually form. The birth of the planets. While the sun was forming at the center of the protoplanetary disk, the remaining gas and dust in the disk began to come together under the force of gravity to form the planets. The process that led to the creation of the planets is known as accretion, where dust and small particles collided and stuck together, gradually forming larger and larger bodies. In the inner regions of the disk, where the temperature was much higher, only the heaviest elements, such as metals and rocky materials, could condense into solid bodies. These materials came together to form the terrestrial planets, such as Mercury, Venus, Earth, and Mars. These planets are made primarily of rock and metal, and they are relatively small compared to the outer planets. In the outer regions of the disk, where the temperature was much colder, gases like hydrogen and helium, along with icy compounds, could condense. These materials came together to form the giant gas planets like Jupiter and Saturn, and the ice giants like Uranus and Neptune. These planets are much larger than the terrestrial planets, and they are composed mostly of gas and ice. In addition to the planets, many other objects formed in the protoplanetary disk. Some of these objects became moons of the planets, while others became asteroids and comets. The process of accretion didn't stop with the planets. It continued to shape our solar system for billions of years. The formation of the moon. One of the most fascinating and unique aspects of our solar system is the formation of Earth's moon. According to the most widely accepted theory, the moon was formed shortly after Earth's formation through a process known as giant impact hypothesis. Around 4.5 billion years ago, a Mars-sized body, often referred to as Theia, collided with the young Earth. The impact was so powerful that it sent large amounts of debris from Earth's outer layers into space. This debris eventually came together to form the moon, the giant. Impact hypothesis explains why the moon is so similar in composition to Earth's outer layers and why it has a relatively small iron core compared to Earth. The formation of the moon had a significant effect on Earth. Not only did it help stabilize Earth's rotation, but it also had an impact on the planet's tides, which played a key role in the development of life. Over time, the moon continued to slowly drift away from Earth, and it now orbits the planet at a distance of about 384,400 kilometers. The solar system stabilizes. After the planets and moons formed, the solar system went through a period of intense bombardment known as the Late Heavy Bombardment, which lasted from around 4.1 to 3.8 billion years ago. During this time, many of the planets, including Earth, were bombarded by large asteroids and comets, which left their marks on the surfaces of the planets and moons. Eventually, the bombardment slowed down, and the solar system began to stabilize. The planets continued to orbit the Sun in their elliptical paths, and the solar system as a whole became a more settled system. Over billions of years, the planets began to cool and form the atmospheres and surfaces we recognize today. The Sun's role in the solar system. The Sun, at the center of our solar system, continues to play a vital role in shaping the conditions of our world. Its energy is responsible for the warmth and light that sustain life on Earth. The Sun also has a profound influence on the motion of the planets and other objects in the solar system. Through the Sun's gravitational pull, the planets are kept in their orbits, and the solar wind, a stream of charged particles emitted by the Sun, affects the atmospheres of the planets. The Sun is currently in the main sequence phase of its life, meaning that it is steadily burning hydrogen into helium in its core. This phase is expected to last for about 10 billion years, and the Sun is currently about halfway through that period. In the future, as the Sun runs out of hydrogen, it will enter the next phase of its life, eventually expanding into a red giant before shrinking into a white dwarf. However, this is still billions of years away. The ongoing evolution of the solar system. The solar system is far from static. Over time, the planets will continue to evolve, and new discoveries will be made. Planets and moons may change, new objects may be discovered in the outer reaches of the solar system, and even more exotic objects, like rogue planets or asteroids from outside the solar system, may enter our cosmic neighborhood. We've already seen some changes in the solar system, including the discovery of exoplanets, planets orbiting other stars, and the detection of Kuiper belt objects and Oort cloud objects, which reside in the far reaches of our solar system. As technology continues to advance, we may uncover even more mysteries about our solar system and our place in the universe. After the formation of the Sun, planets, and moons, the solar system settled into a stable configuration, but this was far from the end of the story. One of the most profound and mysterious events in the history of the universe was yet to come: the emergence of life on Earth. How did simple molecules give rise to complex organisms? What were the conditions that allowed life to take hold in the vast expanse of space? While life did not spring into existence immediately after the Earth was formed, the conditions necessary for life to begin were present in the young planet. The Earth, still cooling from its violent formation, was subject to constant bombardment by comets and asteroids. But at some point, after millions of years of chaos, something remarkable began to happen. Water, a key ingredient for life, began to accumulate in the form of oceans, and the planet's atmosphere became more stable, allowing for the gradual buildup of the conditions necessary for life. The story of life's origins is still one of the greatest mysteries in science, but there are several key factors that are believed to have played a role in the emergence of life. The early Earth. A harsh environment. When Earth first formed, it was a very different place from the world we know today. The planet was extremely hot, with temperatures high enough to melt rock. During the Hadean Eon, the surface was bombarded by constant asteroid impacts, which created conditions unsuitable for life. Volcanic activity was rampant, spewing gases like methane, carbon dioxide, and water vapor into the atmosphere. These gases helped form an early atmosphere, but it was hostile to life as we understand it today. As Earth cooled, water began to condense, eventually forming oceans. These oceans were essential to the development of life, as water is the medium in which biological processes could take place. Without liquid water, life as we know it would not have been possible. The role of chemical evolution. The theory of how life emerged on Earth is rooted in the idea of chemical evolution, the process by which simple molecules became more complex over time. While the exact details are still debated, it is believed that the basic building blocks of life, amino acids, nucleotides, and lipids, formed spontaneously in Earth's early oceans, driven by the energy from volcanic activity, lightning strikes, and solar radiation. A key experiment that supported this idea was the Miller-Urey experiment, conducted in 1953 by Stanley Miller and Harold Urey. They simulated conditions thought to resemble those of early Earth and found that amino acids, the building blocks of proteins, could be formed from simple molecules like methane, ammonia, and hydrogen in the presence of electricity. This demonstrated that the complex organic molecules necessary for life could indeed form under natural conditions. The formation of life's building blocks. Once the basic organic molecules had formed, the next step in the emergence of life was the formation of more complex structures. These molecules, amino acids, sugars, and lipids, came together to form larger molecules like proteins, nucleic acids, such as DNA and RNA, and lipids that make up cell membranes. These large molecules are the building blocks of life, and they combined in increasingly complex ways. One critical development was the formation of self-replicating molecules, most likely early forms of RNA. These molecules were capable of copying themselves and transmitting genetic information to subsequent generations, which is one of the essential characteristics of life. Over time, these self-replicating molecules formed the first cell-like structures, simple membranes that could encapsulate these molecules and allow them to interact in a controlled environment. The first cells, the origin of life. After millions of years of chemical evolution, the first simple cells began to form. These cells were likely prokaryotic, organisms without a nucleus, and would have resembled the bacteria that still exist today. These early life forms were tiny and simple, but they were capable of basic metabolic processes, such as the conversion of energy from the environment into chemical energy. The first cells were likely heterotrophic, meaning that they consumed organic molecules from their surroundings for energy. As life evolved, some cells developed the ability to produce their own energy through a process known as photosynthesis, which uses sunlight to convert carbon dioxide and water into glucose and oxygen. This was a game changer for life on Earth, as it allowed organisms to generate their own energy and began to introduce oxygen into the atmosphere. The emergence of photosynthetic organisms, likely some of the earliest cyanobacteria, was one of the most significant events in Earth's history. Over millions of years, the oxygen produced by these bacteria began to accumulate in the atmosphere, leading to the Great Oxygenation Event, which occurred around 2.4 billion years ago. This event fundamentally altered Earth's atmosphere and allowed for the evolution of more complex oxygen-dependent life forms. The rise of eukaryotes. While prokaryotic cells dominated Earth for billions of years, about 2 billion years ago, a major evolutionary leap occurred. Some prokaryotic cells began to incorporate other prokaryotic cells into themselves, forming a mutualistic relationship. This symbiotic process led to the evolution of eukaryotic cells, which are more complex and contain specialized structures such as nuclei, mitochondria, and chloroplasts. Eukaryotes were the ancestors of all multicellular life, including plants, animals, fungi, and protists. The origin of eukaryotic cells is one of the most significant events in the history of life, as it allowed for the complexity and diversity of life that we see today. The ability of eukaryotic cells to specialize and form multicellular organisms opened the door for the evolution of larger, more complex life forms, including plants, animals, and fungi. The Cambrian explosion, the explosion of life forms. Around 540 million years ago, during the Cambrian period, life on Earth underwent a remarkable burst of evolution known as the Cambrian explosion. During this time, a vast array of new animal forms suddenly appeared in the fossil record. Most of the major animal groups we know today, such as arthropods, mollusks, chordates, and others, can trace their origins to this period. The Cambrian explosion was a pivotal moment in Earth's history, as it marked the rapid diversification of life. The reasons for this sudden increase in biodiversity are still debated, but it is believed that several factors contributed, including the increase in oxygen levels in the atmosphere, the development of new ecological niches, and the evolution of new genetic mechanisms that allowed for the rapid adaptation and diversification of life. The evolution of multicellular life. In addition to the explosion of animal life, the Cambrian period also saw the emergence of the first multicellular organisms, organisms made up of more than one cell. This transition from single-celled to multicellular life was crucial for the development of more complex life forms. Early multicellular organisms were simple, but over time, they evolved into more specialized forms, eventually giving rise to plants, fungi, and animals. The rise of multicellular life opened the door for the eventual emergence of complex ecosystems, systems of interacting species that depend on one another for survival. This process would continue to evolve for millions of years, giving rise to the vast and diverse array of life we see today. The role of evolution in the emergence of life. The emergence of life on Earth was not a single event, but rather a continuous process of evolution. Through natural selection, random mutations, and genetic drift, life on Earth slowly evolved into the complex organisms that populate the planet today. Life adapted to changing environments, developed new strategies for survival, and created the intricate web of life we see in ecosystems around the world. At the heart of this evolutionary process is the concept of genetics, the study of how traits are passed from one generation to the next. It was through the transmission of genetic material that life became more complex and more diverse, eventually giving rise to the rich variety of life forms that now inhabit Earth. As we've seen, the universe began with the Big Bang, an explosion of energy and matter that set everything into motion. Over billions of years, the universe has continued to expand, driven by forces that still puzzle scientists. The very fabric of space itself is stretching, pushing galaxies farther and farther apart. But why is the universe expanding, and how does it continue to evolve? The ongoing expansion. One of the most profound discoveries in modern cosmology came in the late 1920s when American astronomer Edwin Hubble observed that galaxies were moving away from us in all directions. This discovery was based on the observation that the light from distant galaxies was redshifted, meaning that the wavelengths of light were stretched as the galaxies moved away from us. This redshift provided key evidence that the universe itself was expanding. Hubble's observations led to what is now known as Hubble's law, which states that the farther away a galaxy is, the faster it is moving away from us. This suggests that space itself is expanding, causing galaxies to move farther apart over time. The discovery that the universe is expanding was one of the key pieces of evidence that supported the Big Bang theory and forever changed our understanding of the cosmos. The cosmic scale and the rate of expansion. The expansion of the universe is not a simple stretching of space. Instead, it's the result of a cosmic scale factor, which changes over time. In the early universe, the expansion happened incredibly rapidly, especially during a period known as cosmic inflation, when the universe grew exponentially in the blink of an eye, just moments after the Big Bang. As the universe continued to expand, the rate of expansion slowed. The expansion was initially driven by the energy from the Big Bang, but as time passed, the effects of gravity began to counteract the expansion, causing it to slow. However, this slowdown didn't last forever. Around 5 billion years ago, the expansion of the universe began to accelerate. This acceleration is a mystery that still baffles scientists, and it's one of the key areas of study in cosmology today. The force responsible for this acceleration is believed to be dark energy, a mysterious and invisible force that seems to be pushing galaxies apart, causing the universe to expand faster over time. What is dark energy? The discovery of the accelerated expansion of the universe led to the identification of dark energy, a force that makes up about 68% of the universe's energy content. Unlike regular matter or even dark matter, dark energy is not something that can be directly observed. It doesn't emit light, interact with particles, or have any detectable form that we can easily study. But its effects are clear. It is responsible for the current accelerated expansion of the universe. The nature of dark energy is one of the greatest mysteries in modern science. Some theories suggest that dark energy is a property of space itself, with space acting as a sort of energy field that stretches as the universe expands. Others propose that dark energy could be related to quantum fluctuations in the vacuum of space. Despite our current lack of understanding, dark energy plays a crucial role in the future of the universe and is one of the key drivers of its expansion. The fate of the universe. As the universe continues to expand, the questions arise. How far will it stretch? Will it ever stop expanding? And how will it all end? These are some of the most fundamental questions in cosmology, and scientists are still working to find answers. There are several possible scenarios for the future of the universe, each depending on factors like the amount of dark energy and the shape of space itself. 1. The Big Freeze. The most widely accepted theory about the fate of the universe is the Big Freeze. In this scenario, the universe will continue expanding at an accelerating rate, pushing galaxies farther and farther apart. As the expansion continues, stars will burn out, and galaxies will become isolated from one another. Over trillions of years, the universe will become colder and colder, and eventually, all the stars will have exhausted their fuel. The universe will be left in a state of darkness and near absolute zero temperature. This is the Big Freeze. 2. The Big Crunch. In contrast to the Big Freeze, another possibility is the Big Crunch. This scenario suggests that if the density of matter in the universe is high enough, gravity could eventually halt the expansion and cause the universe to collapse inward. In this case, galaxies, stars, and planets would be pulled back together, eventually collapsing into a singularity, a point of infinite density. This is the opposite of the Big Bang, and it could mark the end of the universe as we know it. However, the Big Crunch seems less likely in light of current observations, which suggest that the universe's expansion is accelerating rather than slowing down. While the idea of the Big Crunch was once considered a possible fate for the universe, it is now less favored by scientists. 3. The Big Rip. Another possibility, though more speculative, is the Big Rip. In this scenario, the expansion of the universe continues to accelerate at such a rapid pace that it eventually tears apart galaxies, stars, planets, and even atoms. The force of dark energy could become so strong that it overcomes the forces holding matter together, causing the universe to unravel completely. This would be a violent and dramatic end to the universe, where everything is torn apart by the very forces that were once responsible for its expansion. The expansion. Beyond our observations. As the universe continues to expand, certain regions of space will eventually move beyond our ability to observe them. Due to the acceleration of the universe's expansion, the light from distant galaxies will become increasingly redshifted, meaning that it will be stretched to longer wavelengths, making it harder to detect. Eventually, galaxies that are currently observable will be pushed so far away that their light will no longer reach us. This means that in the distant future, observers on Earth will no longer be able to see galaxies beyond our local group, and the night sky will appear empty. In a few billion years, the Andromeda Galaxy, our closest galactic neighbor, will collide with the Milky Way. This event, while destructive for the stars and planetary systems involved, won't have the same catastrophic effect as a galaxy's end. Rather, stars will pass by each other, and new stars may form in the chaos of the collision. The merger will likely create a new, larger elliptical galaxy. But after this, as the universe continues to expand, our view of the cosmos will become more and more limited. The expanding universe and time. The expansion of the universe is not just a physical phenomenon, it also changes how we understand time itself. As space expands, distances between objects increase, meaning that events in distant parts of the universe happen at different rates. Over immense distances, the passage of time appears to slow down, a concept rooted in relativity. This phenomenon is known as cosmological time dilation, and it means that faraway objects appear to move more slowly as the universe expands. The further away a galaxy is, the faster it appears to recede from us, and this has profound implications for our understanding of the cosmos. The mysteries of dark matter. While dark energy drives the expansion of the universe, dark matter plays a crucial role in shaping the universe's structure. Unlike dark energy, which accelerates the expansion of space, dark matter exerts gravitational pull on visible matter, helping to form galaxies and galaxy clusters. Though we cannot see dark matter directly, scientists can observe its effects on the movement of galaxies and galaxy clusters. Dark matter is thought to make up around 27% of the total mass-energy content of the universe, and understanding it is crucial to understanding the expansion of the universe. As we continue to explore the vastness of the universe, we encounter two of its most mysterious and elusive components: dark matter and dark energy. These substances make up about 95% of the total mass and energy content of the universe, yet we can neither see nor directly detect them. They remain two of the greatest puzzles in modern cosmology, shaping the structure of the universe and its future expansion. What is dark matter? The first of these mysterious substances is dark matter, which is thought to make up about 27% of the total mass-energy content of the universe. Unlike ordinary matter, which interacts with light and can be observed through telescopes, dark matter does not emit, absorb, or reflect light. This makes it completely invisible to our current observational techniques, which rely on detecting electromagnetic radiation, like visible light, radio waves, and X-rays. Yet, dark matter can be detected indirectly because of its gravitational effects on visible matter. Scientists first proposed the existence of dark matter in the 1930s, when Swiss astronomer Fritz Zwicky noticed that galaxies and clusters were moving much faster than could be accounted for by the visible matter in the clusters. The extra gravitational pull required to keep these galaxies from flying apart could only be explained if there was some unseen mass in the clusters. Zwicky's observations were the first hint that the universe contained more mass than we could see. Today, dark matter is known to exist in vast quantities, but we still don't know exactly what it is. Some of the leading candidates for dark matter are: 1. Weakly interacting massive particles, WIMPs. These are hypothetical particles that interact only via gravity and the weak nuclear force, making them extremely difficult to detect. 2. Axions. These are very light theoretical particles that could account for the dark matter seen in the universe. They were proposed to explain certain phenomena in quantum mechanics and particle physics. 3. Sterile neutrinos. These are hypothetical particles that are a heavier form of neutrinos, which could be involved in dark matter interactions. Though we haven't directly detected dark matter, its presence is inferred from its gravitational effects on galaxies, galaxy clusters, and the cosmic microwave background, CMB. Dark matter helps hold galaxies together and prevents them from flying apart, as its gravitational pull provides the additional mass necessary to explain the motion of galaxies within clusters. The role of dark matter in the formation of the universe. Dark matter plays a critical role in the formation of structures in the universe. In the early universe, when the cosmos was much smaller and hotter, tiny fluctuations in the density of matter existed. Gravity, aided by dark matter, began to pull these denser regions together, forming the first stars, galaxies, and galaxy clusters. Without dark matter, the pull of gravity wouldn't have been strong enough to create the vast structures we see today. Dark matter also acts as a scaffold for the formation of galaxies. It doesn't form stars or emit light, but it exerts gravitational forces that pull together gas and dust to form galaxies. These invisible halos of dark matter surround galaxies, helping to hold them together and preventing them from flying apart as they rotate at high speeds. Without dark matter, the universe would look vastly different, with galaxies unable to hold themselves together. What is dark energy? The second great mystery of the universe is dark energy, a form of energy that accounts for about 68% of the total energy content of the universe. Unlike dark matter, dark energy does not exert a gravitational pull. Instead, it seems to push galaxies apart. Dark energy is responsible for the accelerating expansion of the universe, a discovery made in 1998 by two independent teams of astronomers studying supernovae. Dark energy is theorized to be a property of space itself. The more space there is, the more dark energy there seems to be. This idea is similar to the concept of the vacuum energy predicted by quantum mechanics, where even empty space contains energy. The leading hypothesis is that dark energy is a kind of anti-gravity force that works against the attractive force of gravity, driving the expansion of the universe. While dark matter's gravitational effects slow down the expansion of the universe, dark energy accelerates it. This is why the universe's expansion, which began slowing after the Big Bang due to gravity, started speeding up again about 5 billion years ago. The exact nature of dark energy is still unknown, and understanding it is one of the biggest challenges facing modern physics. The effect of dark energy on the future of the universe. The presence of dark energy has profound implications for the future of the universe. If the current rate of acceleration continues, it could lead to one of several possible outcomes. 1. The Big Freeze. This is the most widely accepted scenario. As dark energy pushes galaxies farther apart, the universe will continue to expand at an ever-increasing rate. Stars will burn out, galaxies will drift away from each other, and the universe will become colder and darker. Over trillions of years, all stars will burn out, leaving only remnants of cosmic matter scattered across an increasingly cold and empty universe. This process could continue until all that remains are the dead remnants of stars and black holes, a universe frozen in time. 2. The Big Rip. If the expansion of the universe continues to accelerate, dark energy could eventually overcome all the forces that hold matter together, including the gravitational forces between galaxies, stars, planets, and even atoms. This scenario, known as the Big Rip, would tear apart galaxies, stars, planets, and even atoms, resulting in a catastrophic end to the universe. While this scenario is more speculative, it remains a possibility depending on the properties of dark energy. 3. The Steady-State Universe. Another possibility, though less likely, is that the universe will continue to expand at a steady rate, with dark energy remaining constant. In this scenario, the universe would gradually become increasingly sparse, but it wouldn't undergo any dramatic changes. Galaxies would continue to drift apart, but at a slow, steady pace. The role of dark matter and dark energy in the big picture. Dark matter and dark energy are the dominant forces shaping the structure and future of the universe. Together, they make up about 95% of the total mass and energy content of the cosmos, yet we still have much to learn about them. Dark matter shapes galaxies, galaxy clusters, and the overall structure of the universe, providing the necessary mass to hold everything together. Without dark matter, the formation of stars and galaxies would have been much slower, and galaxies would not have been able to hold themselves together. Dark energy, on the other hand, drives the accelerating expansion of the universe, and it will determine the ultimate fate of the cosmos. Whether the universe will continue to expand forever, collapse back in on itself, or tear apart in a big rip remains uncertain. But one thing is clear. The interplay between dark matter and dark energy is essential to the universe's past, present, and future. The search for dark matter and dark energy. Despite their enormous influence, dark matter and dark energy remain largely invisible and undetectable. Scientists around the world are working tirelessly to uncover their secrets. Observatories like the Large Hadron Collider and the Fermilab in the United States are searching for clues about dark matter by colliding particles at high energies. Meanwhile, scientists are also investigating dark energy by studying the cosmic microwave background radiation and the behavior of distant supernovae. The search for dark matter and dark energy is one of the most exciting areas of research in modern physics, and new discoveries may dramatically alter our understanding of the universe. As we continue to explore the cosmos, it is likely that we will uncover more mysteries and reveal the fundamental nature of these invisible forces that govern the universe's structure and future. The universe, born from the Big Bang, has undergone dramatic changes over billions of years, and it will continue to evolve for billions more. Understanding the future of the universe is one of the most profound questions in cosmology. Will it continue expanding forever? Will it collapse in on itself? Or will it meet some other end, entirely different from what we expect? The future of the universe depends on the balance between several key forces, including the influence of dark energy, dark matter, gravity, and the fate of the stars and galaxies. As we explore the potential outcomes for the universe's future, We'll delve into the possibilities of how it will evolve and what it might look like in the distant future. The continuing expansion of the universe. For the past several billion years, the universe has been expanding, and this expansion is not slowing down. In fact, the universe is accelerating in its expansion due to the presence of dark energy, which is pushing galaxies farther apart. This accelerated expansion suggests that, for the foreseeable future, the universe will continue to stretch out, with galaxies moving farther and farther from each other. But how long can this expansion continue? The current data suggests that the universe will continue to expand indefinitely, though the rate of expansion may change as the effects of dark energy and other factors become more pronounced. This continuous expansion means that in the far future, the universe will become increasingly sparse, with galaxies, stars, and other cosmic structures becoming isolated from each other. This scenario, known as the Big Freeze, suggests that the universe will grow cold and empty over time as stars burn out and galaxies drift farther apart. The fate of stars. The stars in the universe are the engines of its evolution, and their life cycles will play a crucial role in determining the future of the cosmos. Stars are born from clouds of gas, live for billions of years, and eventually die, sometimes in dramatic explosions called supernovae. But what happens to stars in the distant future? 1. The Sun's fate. Our Sun, like all stars, is not eternal. It is currently about 4.6 billion years old and is in the main sequence phase of its life, during which it burns hydrogen into helium through nuclear fusion. The Sun has enough hydrogen to continue this process for about another 5 billion years. As it approaches the end of its life, the Sun will begin to run out of hydrogen in its core. At this point, it will expand into a red giant, a massive star with a diameter that will likely engulf the inner planets, including Mercury, Venus, and possibly Earth. In its red giant phase, the Sun will start fusing helium into heavier elements like carbon and oxygen. Eventually, it will shed its outer layers in a planetary nebula, leaving behind a dense hot core known as a white dwarf. This white dwarf will continue to cool over the course of billions of years, becoming an increasingly dim object. 2. The death of other stars. For other stars, the fate depends on their mass. Massive stars, much larger than the Sun, live fast and die young. These stars burn through their fuel quickly and end their lives in spectacular supernova explosions, releasing vast amounts of energy and scattering heavy elements into the surrounding space. After the explosion, what remains can form a neutron star, or, if the star is massive enough, collapse into a black hole. These supernovae are crucial to the evolution of the universe because they distribute elements like iron, gold, and uranium into space. These elements are necessary for the formation of planets and, eventually, life. After the supernova, the remnants of the star may remain as a pulsar or a black hole, both of which are fascinating objects in their own right. 3. The end of star formation. As time goes on, the universe will run out of the gas necessary to form new stars. The raw materials for star formation, hydrogen and helium, will become increasingly rare, and the birth of new stars will slow down. As stars continue to burn out and explode, there will be fewer and fewer stars remaining. Eventually, the universe will be a place where only the oldest stars remain, and the cosmos will become a place of quiet, fading embers with few stars still shining. The fate of galaxies. As galaxies continue to expand, they will drift farther and farther apart. However, galaxies are not destined to remain isolated forever. In about 4 billion years, the Andromeda Galaxy, our nearest large galactic neighbor, is expected to collide with the Milky Way. This collision will not be violent in the way we might imagine. In fact, individual stars are unlikely to collide directly, since stars are separated by vast distances. However, the gravitational interaction between the two galaxies will dramatically reshape both of them, likely resulting in a larger, elliptical galaxy. Over time, galaxy mergers will become more common, and as galaxies merge, new stars will be born from the gas clouds that are compressed during these collisions. But eventually, this process too will come to an end as the universe continues to expand and galaxies become isolated. The role of black holes in the universe's future. One of the most intriguing aspects of the universe's future is the role that black holes will play. As stars die and galaxies collide, black holes are expected to become even more central to the evolution of the universe. Some of the most massive black holes are found at the centers of galaxies, and these supermassive black holes will continue to grow as they consume matter from their surroundings. In the distant future, the remnants of galaxies, including black holes, may dominate the universe. Supermassive black holes, with masses millions or even billions of times that of the Sun, will likely be the last remaining active objects in the cosmos. These black holes will continue to consume matter and grow, but eventually, even they will lose their energy. One theory suggests that black holes may eventually evaporate through a process called Hawking radiation, named after physicist Stephen Hawking. According to this theory, black holes slowly lose mass and energy by emitting radiation, and over incredibly long timescales, they may eventually shrink and vanish entirely. The Big Freeze. The ultimate fate of the universe? If the expansion of the universe continues at its current accelerated rate, the Big Freeze may be the ultimate fate of the cosmos. In this scenario, galaxies will continue to move farther apart, and the universe will become increasingly cold and empty. Stars will burn out, and the light from distant galaxies will fade, leaving the universe in a state of near absolute darkness. As stars burn out, their remnants will scatter across the vastness of space. Black holes will remain as the final beacons of light, but even they will eventually fade away over billions of years. In this distant future, the universe will have become a dark, frozen place with little to no activity or light. The search for new frontiers. Despite this seemingly inevitable fate, the universe still holds many mysteries waiting to be discovered. The search for new planets, exoplanets, and the potential for life beyond Earth continues to capture the imagination of scientists and astronomers. Advances in technology, like the James Webb Space Telescope, will allow us to peer even farther into space, searching for distant galaxies and studying the evolution of stars and planets in ways we never could before. The human spirit of exploration continues to drive our desire to understand the cosmos. Whether through the search for life on other planets or the study of the farthest reaches of space, humanity's quest to understand the universe will continue to shape the future. Conclusion. The ever-evolving cosmos. The future of the universe is a journey that spans billions of years, and although the exact outcome is uncertain, one thing is clear. The cosmos is always changing. Whether it continues expanding forever, eventually collapses in on itself, or meets some other fate, the universe will continue to evolve. From the Big Bang to the birth of stars, from the formation of galaxies to the eventual death of stars and the cold, dark fate of the cosmos, the universe is a place of constant transformation. As we look to the future, we can only imagine the incredible journey that lies ahead and the scientific discoveries yet to be made. The universe, in all its mystery and grandeur, is a never-ending story, one that will unfold long after our time has passed.